Hi there, Andrew Dunkley here. Thanks for joining us on Space Nuts Q&A. Good to have your company. Coming up, we're doing a bit of homework. You might remember a couple of episodes ago, Alan was asking about the detectability of light at 1 candle power of an LED in space. Fred has done it for you, Alan. We're also going to be looking at bolometric luminosity, Hawking radiation, major space hazards, and what do you do if you need to fix something on the James Webb Space Telescope? We will tackle all of those questions on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again. It's Professor Fred Watson, astronomer at large. Hi, Fred.
Hello, Andrew. Fancy seeing you here.
Yes,
with the telescope behind you.
Yes. Oh, there it is. Yeah, you can see that, can't you?
Yeah.
It's pointing up at the sky right now, which is blocked by a big roof, making it quite useless. Although I don't know if you noticed, but it's got a sun filter on it.
Yes, I did see that. Yeah.
I went out the other day and I had a bit of a squiz at the disk of the sun, and I could actually see little sunspots.
Yeah.
Amazing.
Yep. It's always worth a look.
Yeah, it is. So you've got to be very careful when you're looking at the sun. Actually, I did have the filter off at one stage, and I just must have passed my face over the eyepiece, and I just found that streak of heat crossing my face.
Yeah, you would. Yeah.
It caught me quite off guard. I'm glad I didn't put my eye over the eyepiece at that point in time. Fred, we have a bit of homework for you to deal with. Alan contacted us the other day about the detectability of light at 1 candle power of an LED in space, and we discussed the fact that light travels basically forever, and but Alan's question was more about how far would be too far not to be able to see it at that power.
I think I've got a feeling Alan mentioned the Hubble Telescope as well. Maybe not. That might be my imagination. But the bottom line is, let me rephrase the question then. How far away could you see a 1 candle power LED with the Hubble Telescope? I think it was something like that in Alan's question. And so you've got to basically make a few assumptions on this, and I made some very rough and ready ones. But checking the literature, checking the interweb, got the impression that you would be able to see with the naked eye and good eyesight. You're talking now top-class eyesight of a young person, not an old gimmer like me. The detectability of a one candle power LED with your unaided eye would be. I've seen suggestions up to 2 kilometers, but I think I think that's pretty optimistic. I settled on 1 kilometer, and that makes life very much easier for the rest of the calculation. So if you could just see this candle at a distance of 1 kilometer, or this 1 candle power LED, that if you can just see it, that means it's got the magnitude of a 6th magnitude star. And you remember we in the trade measure star brightness in magnitude, and the numbers go the wrong way. So 1st magnitude star is a bright one. Geordie likes 1st magnitude stars. You can tell.
Absolutely.
This goes back to the ancient Greeks, actually, stars of the 1st magnitude. But we now, having set up a measuring system for that, we know that there are some stars that have negative magnitudes, like the brightest star in the sky, Sirius, if I remember rightly, is minus 1.8 or thereabouts. I think it's a very bright object. But typically, the faintest thing you could see with the unaided eye would be the 6th magnitude. Now, assuming that the faintest thing that the Hubble Telescope can see is about the 30th magnitude, and I think that's in the right ballpark, doing some rough and ready calculations, which I might have got completely wrong because I did them this morning while I was thinking about breakfast. The answer I got was that the Hubble Telescope would be able to detect, it's not as far as you might think, actually. It would be able to detect a 1 candle power lamp at a distance of 63,000 kilometers.
Oh, wow.
Yeah. I thought it would be more than that.
Yeah.
But it's, and that's about, a sixth of the distance to the moon. So you would not be able to see a 1 candle power LED at the distance of the moon, even with the Hubble telescope. You might do it with the Webb, actually. I should have done the calculation for the Webb as well. Anyway, that's the bottom line. I hope I've done that calculation correctly. Right. But yeah, it's not as far as you might think.
No, not at all. All right, Alan, hopefully that solves your little puzzle. Thanks for sending that in the other day. Let's go to some audio questions now. This one comes from Nate.
Hey guys, Nate from the Glasshouse Mountains in Queensland here. Been listening for about a year now and love the podcast. I'm currently doing a postgrad in astronomy at Swinburne, and recently we were discussing bolometric luminosity, which is the stellar measurement of wavelengths across the entire electromagnetic spectrum, not just the visible portion. Now, we have an equation for this, and it got me wondering whether there's some sort of a bolometric standard for when a star goes through a major change. I'm not quite sure I know the right words to phrase the question properly, but an example might be, is there an equation or standardized way to predict the bolometric luminosity of, let's say, a supernova before the supergiant explodes, or is it completely dependent upon the classification or stage of life of the star beforehand? And then on the flip side of that, is there such a thing as bolometric decay? So I guess using the same example as before, do certain wavelengths that arise from something like a supernova decay at different rates compared to others? Or again, is it just completely dependent on the classification or stage of life of the star before it goes bang? I hope that made sense. Keep up the great work, guys, and thanks for giving my questions a go.
Thanks, Nate. Didn't make sense. Next question. Honestly, that one really was a mind bender for me. I'm pretty sure you've got a better idea of what he was talking about, Fred.
It's a great question, a highly technical question that needs a bit of unpicking, if I may. If Nate will excuse me while I talk about the background to this, and that is that bolometric brightness is the brightness of something measured over its whole spectrum. So it goes from, the gamma ray spectrum right out to the long wavelength radio spectrum. So if you're making a bolometric measure, you're measuring all the radiation. And there's a machine that does that, or a device that does that. It's called a bolometer. And bolometers, in principle, are very simple. It's a bit of metal with a wire attached, cooled down to nearly absolute zero. They're used principally in microwave telescopes like the James Clerk Maxwell Telescope in Hawaii, like ALMA, the Atacama Large Millimeter Array Telescope. So, and there's a reason for that. Even though a bolometer in principle could be used across the whole spectrum, it turns out that, if you want to measure, the brightness of light or the brightness of X-rays or anything, there are far more sensitive methods of doing that than using a bolometer. But in the microwave region of the spectrum, a bolometer is all you've got, and that's the best way to do it. So that's just sort of discussing a little bit about where bolometry comes in.
Honestly, Fred, I've got to tell you that a bolometer sounds like something Monty Python made up.
Yeah. Well, it's funny you should say that, because the original paper for bolometers was Cleese et al.
Oh, you're kidding?
No, I'm kidding. I'm kidding.
Oh, okay.
Making it up as I go along.
That was well delivered, though, I must say. Me, Phil, that wouldn't be hard.
No. Anyway, it's a strange word. That's right. I should check its origins. It's probably Greek in origin. But it basically means you're measuring the whole spectrum, and so you can set up bolometric equations and things of that sort, as Nate mentions. Now, similarly to what I've just said about there being better ways than looking at the bolometric system to measure the brightness of stars and things of that sort using different kinds of detectors, I think it's probably true that in the situation that Nate is talking about, where you've got a star that's kind of not very far off going supernova, and has symptoms in its light, what you'd be doing, you would be looking at the spectrum analysis. You'd really be looking in detail, probably at the visible spectrum, because that's the richest region of the spectrum in diagnostic features. The atomic and molecular lines are what we call absorption lines. They're the sort of fingerprint of different elements and molecules, that kind of barcode that we see across the spectrum of a star or galaxy. That would be a much more telling way of looking at the way the star is evolving than its sort of bolometric magnitude. And I'm not sure whether I'm answering the question that Nate is expounding or postulating, but I think that would be the answer anyway, that you would always look for much more sensitive symptoms or fingerprints that something was going to happen in a star, highly evolved star, one near the end of its life that's about to go supernova. I think you would be thinking about the ratios of elements and things of that sort rather than looking at the bolometric equation. I hope that answers the question, Nate.
Yeah, he also asked about bolometric decay. Is there such a thing?
Well, yes. So there probably is, but I think there are other markers that will be much more sensitive than bolometric decay, if I can put it that way.
All right, fair enough. And bolometric comes from the Greek bol ray. There you are. So
Meaning
you were
what?
right. Bol ray.
Yeah.
Meaning bolometric, I think. Hang on, look, I've lost it now. Word origin. Bol from the Greek bol ray, bolometric. Yeah, and there's all sorts of variations on it. So bolometer is the English word of the Greek. Hang on, I keep getting pop-ups. Bolometric, bolometrically, bolometry, from the Greek bol ray of light stroke, from balling to throw, plus or minus meter. That didn't make any sense to me whatsoever. I just quoted that straight from the Collins Dictionary.
Yeah. So, well, okay. Yeah.
Anyway, it's Greek origin. That's all we really wanted to figure out.
Yeah. So bol is the Greek word for array. Is that what?
Now I've got to find it again. Yeah, it's here somewhere.
All right.
Well, it's written in Greek, so I can't tell you what it says.
Oh, it's all Greek to me, Andrew.
Yeah.
We should just let's leave everybody to look it up themselves.
Yeah, someone send us a note because I'm done with that.
And yeah.
It's hurting my brain. Thank you, Nate. Great question, really deep. And my pharmacist will be selling me something to fix my head after listening to that one. Let's go next to David.
Hi guys, David from Melbourne here. Stephen Hawking theorised the existence of Hawking radiation, and I've been wondering, could this have anything to do with dark matter or dark energy? Anyway, love the show. Thanks. Bye.
Thanks, David. We get this one a lot, don't we? Is Hawking radiation anything to do with dark matter, dark energy? What's the usual answer? Maybe, maybe not.
The usual answer would be no, because Hawking radiation it just kind of seeps out of black holes with not really much energy. It's electromagnetic radiation. Probably means you need a bolometer to look at it, but so slow and so low intensity that it's hard to imagine that Hawking radiation as such would contribute to dark energy. But we have had this research done recently that you and I spoke about, Andrew, that does link black holes to dark energy. And I have to say, I can't remember the mechanism which was being proposed in that, but I don't think it involved Hawking radiation. I think it was something much more
that's a simple
subtle.
answer.
I think it was gravitational decay, yeah. So the answer is no, but black holes may play a part in dark energy.
Okay. There you go, David. Simple one, a big NO, or maybe a little one, because this is astronomy. Sometimes we've got a definite idea of something that turns out to be not the right answer in the
that's right.
long run anyway.
Completely wrong answer.
But at this stage, no. At this stage, no.
That's the way to
thank
say
you, David.
it,
Yes. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Moving right along, Fred, our next question comes from a regular contributor who we will call Martin.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres from Potomac, Maryland, USA. And I've been busy launching glycine elephants at the moon Titan and putting them on comets, of course. And, well, believe me, it's tricky getting those elephants onto those comets. How the elephant got into the comet, I'll never know. But my annoying frenemy, Egon Rusk, wants to know what are the major hazards to his near light speed spacecraft as it approaches C, the major hazards to the traveling humans and the biosphere. Can't wait for the answer. Berman Gorvine, over and out.
Thanks, Martin. I'm assuming he's referring to a science fiction novel in that first part.
I think so, yes. I think that's right. Which is probably simultaneously in many genres. Yeah, that's interesting.
Possibly so, indeed, yes. But the question was hidden in there somewhere about his now I'm trying to think of it. My brain's not working well today. What was his question?
It's all about what are the difficulties of something as you approach the speed of light if you're a space traveler. Yeah, what are the space hazards? And actually, interestingly, we had a similar question last time, I think, where one of our questioners asked whether you need to streamline your spacecraft when you're traveling at relativistic velocities so that you don't get too much drag from the interstellar medium. Do you remember that?
That's right, we did too. That was a couple of weeks ago, yeah.
Yeah, but one correlation of that was that as you approach the speed of light, you're talking about particle accelerator speeds. And so, if you think of your spacecraft traveling near the speed of light, this is for Martin, maybe what would happen is the particle content of the interstellar medium, or if you're in the solar system, the interplanetary medium, would be at such high energies that you would get nuclear interactions in the walls of your spacecraft. So, you hit a subatomic particle at nearly the speed of light, and you get all these you get the collision that generates subatomic particles of different species. It's how the things like the Large Hadron Collider work, and some of those might be quite dangerous. There might be gamma radiation comes off or something of that sort. So I'm speculating here wildly rather than basing this on firm scientific knowledge. But there could be dangers from radiation because of the effects of the interaction of your spacecraft with the basically the solar wind, the interstellar medium, the interplanetary medium. So just watch out for that, especially if you're carrying elephants with you. That could really make it a tricky business.
Yeah, they've got pretty thick hide though. I think they'd probably
that's true.
do
Yes,
better.
they may make natural radiation shields. Who knows?
Yeah, and they're already packed because they're carrying a trunk.
I like that one. I like that one.
Oh,
That's very
gosh,
good.
I had to do it.
Yeah,
Had to do
very
it.
good one.
But yeah, my first thought when I listened to Martin's question in rehearsal the other day was radiation. My first thought was radiation. So
Well, there you go. You're on the money.
It could be, well, I'd say it's one of the major hazards regardless in space. I mean, it's a hazard on the moon just by being on the moon. It's a hazard on Mars.
Yeah.
You can't live on the surface unprotected. So traveling in space, especially at those relativistic speeds, opens up all sorts of possibilities. Yeah, it's one thing to talk about reaching the speed of light in terms of travel, but you've got to think about the consequences of doing it. Not only warping time, but waking up things that you ought not to be playing with, I think.
Yeah, maybe so. Maybe so.
Thank you, Martin. Always good to hear from you. And our final question comes from Ryan.
Hey, guys. It's Ryan from Townsend, Delaware again. I had a question about the James Webb Space Telescope. I know that it has a limited amount of fuel and a limited lifespan, but did they design in anything that would allow a secondary craft to come out and, top up the tanks and keep it going? Thanks as always. Keep up the good work.
Well, we know that after Hubble was launched, they were able to send a space shuttle up there to fix a problem with, I think it was the lens or the focus or something. There was a problem there. But I think when you and I started talking about James Webb, it was all about getting it exactly right, straight up, because once it was out there, that was it. All bets were off.
That's correct. That's right. And that's because of where it is. So you're right, Andrew. The Hubble mirror was the most perfect mirror ever made, but made to the wrong prescription because of an accident in testing. We understood in the end what had happened, and that was corrected, at least partially, by means of a little correcting lens system that was sent up. And as you say, it was repaired. It was repaired again late in the shuttle's career, the shuttle system's career, with new gyros being provided for it, because that's the problem.
I remember that. Yeah.
That was probably around 2011 when the shuttle program was winding down. The reason for that was the shuttle was the only spacecraft able to reach the altitude of the Hubble Telescope, which I think is 600 kilometers or maybe 700. And the shuttle could do that, but the other spacecraft available, which was actually principal science capsules, couldn't. I'm not sure where we are now with that, actually, whether something like the Boeing Starliner, which we're still waiting for its test launch, first one with astronauts, or the Crew Dragon spacecraft, whether that would be capable of reaching the Hubble's altitude. But I think that's unlikely. I think the next thing that might rendezvous with the Hubble will be a robotic spacecraft that will be designed to bring it down, maybe probably in a no-controlled, in a controlled burn-up into the atmosphere. The original plan with the Hubble was it was going to be brought back to Earth by space shuttle and put in a museum.
I would have thought so, yeah.
Yeah, but with the space shuttle being retired in 2011, that option has gone. We, at the moment, haven't got anything big enough to bring it back, although in the end, maybe Elon Musk's Starship might have a cargo version that would let you do that. I don't know the answer to that.
Well,
anyway,
he's making cargo versions of Teslas these days, so why not?
Yeah, that's right. We saw one actually when we were in the US. One of his, forgot what it's called. It's got a funny name.
Truck.
It's a truck. Yes, it's like a ute with a kind of science fiction name, which eludes me at the moment. But anyway, saw one in Gruner in Texas.
How about that?
I'm usually called Green.
Interesting side note that a lot of Australians would be aware of, but maybe not too many others. The ute, the utility, was an Australian invention.
There you go. Yeah. But getting to the point of Ryan's question, The thing about and you've put it in a nutshell already, Andrew. The James Webb Space Telescope sits at the L2 point, the Earth's second Lagrange point in relation to the Sun, which means it's 1.5 million kilometers on the side of the Earth away from the Sun. And certainly with present technology is unreachable by humans. Whether you could mount a robotic mission to refuel or repair is an economics question. And certainly the thinking at the beginning of the James Webb's mission was that it would cost more to set up a mission to repair it or to put extra fuel in the tanks, of which we think there's about 20 years worth, by the way, and this is to maneuver it to keep it pointing in the right direction. It will be more expensive to do that than to just build another one and send that up into orbit. So the normal philosophy on the Webb is that if anything goes wrong, that's the end of the story, and you think about what comes next.
Yeah, which makes me wonder, obviously it carries fuel, 20 years worth to keep it in position. So when it runs out of fuel, what will happen to it? Will it just sort of get flung around a bit or just spin off into oblivion, or how will that affect it?
So it will, yes. So its orbit will. It's currently in orbit around an imaginary point.
Yes.
It orbits the L2 point, the stable point caused by the balance of the Earth's and the Sun's gravity, and the Earth's motion around the Sun. So what would happen would be it would just kind of drift off away from where you want it. It will be subject to gravitational forces of the planets, principally Jupiter, which will disturb its orbit. And so it will kind of hang around. The risk is that it's uncontrolled. There are several other bits of hardware up at that L2 point, including the Planck spacecraft, which measured the cosmic microwave background radiation. So that would be then seen as a hazard to shipping. You might want to boost it into what's called a graveyard orbit, which is somewhere where it's out of the way and isn't going to interfere with anything. So yes, it's
maybe they built that into the planning.
Probably.
Who knows? Yeah.
I'm sure that's true.
Well, there is a requirement these days, isn't it, that if you put something into space, it's your responsibility to bring it down safely or deal with it according to those parameters.
Deal with it.
So I don't know if it would apply to James Webb because it's not in orbit around the planet, but I would assume so. Okay. Thank you, Ryan. The answer's another one that we've got a few hard no's this week on some of the questions, but that happens from time to time. But no way of refueling or fixing the poo-poo valve if it breaks. It's all on its own out there. And thanks to everybody who contributed this week to Space Nuts Q&A. Really appreciate your questions. We've just received a new batch, so we'll be going through those, and we'll have plenty to talk about in forward episodes. But don't let that discourage you from sending questions in via our website, spacenutspodcast.com or spacenuts.io, and have a look around while you're there. Buy a couple of books from Fred. He needs the money for his landscaping. And and all of that. Thank you, Fred, as usual. It's always great fun.
It's a pleasure, Andrew.
There's a big hesitation there. I'm not sure.
No, it's a pleasure. Just trying to juggle a few things at once here. I can only do one thing at a time. That's the problem.
Yeah, me too. And thinking's not one of them that ever happens.
That's right. That's right. Yeah.
All right. See you, Fred. Thank you.
Cheers for now. Talk soon. Bye-bye.
Fred Watson, astronomer at large, and Hugh in the studio, who sent us those questions. We're going to have to do a bit more vetting, Hugh. I think they were too hard. And from me, Andrew Dunkley, thanks for your company again. We'll catch you on the next episode of Space Nuts. Bye. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.